So, if you have this, let me redraw this. If you start with this, let's look on this on the edge now. If I have something like this, a halogen, or a, what does it say, a halogen? Put X here for a halogen. And let's put a hydrogen here, and a methyl here, and a hydrogen here, and an ethyl group here. If I had a weak base, like water, this is going to go by the E1, and I say E1 mechanism. I'm going to get a mixture of two products. I could get the double bond forming I could lose this halogen and this hydrogen. If that happens, you're going to get double bond forming here. We'll still have this methyl group. We'll still have the hydrogen here. Remember last week, I think I gave you an art lesson. Typically, if it's sp3 hybridized, they'll draw the groups up and down like this. This carbon is sp3 hybridized. I see these are all sp3 hybridized. If it's sp2 hybridized, then this is all in the same plane. This methyl group, this hydrogen, all these, they're in the same plane as the ring. So I usually draw it out like that. I'm not going to take off and draw it differently. That would be one product. But then the other product you're going to get, this is dehydrohalogenation. You lose this halogen and this hydrogen. Okay? And so the other product you get, if I say it's E1 mechanism, usually it's a weak base. You're going to get the double bond here. And you will have the ethyl group. And see, we lost a hydrogen. We have a hydrogen here. So you get a mixture of two products. And the reason is, in the E1 mechanism, remember the slow step is the halogen first leaves. If that halogen leaves, then this will have a plus charge. This carbon will be sp2 hybridized. Just remember to have this on. Supposing I'm being recorded if I put this on. I don't know if it's true or not. Not to get maybe we'll see. A couple students who came through the class and wanted to record. Okay, I'm here. All right. Too bad. Anyway, this is flat. This is sp2 hybridized carbon. So now the base can come in from the top or from the bottom. Okay, it comes in from the top, we can pull off this hydrogen, it comes from the bottom. Come in from either side. There's no restrictions whatsoever. So you're going to get these two products, this one and this one. So just keep this in mind, make a mental note. E1 mechanism. The groups that are leaving don't have to be in any special location. Okay? It can be, because there's not a top and bottom, they're not opposites. They just, here's the top and the bottom. This is flat. Okay? All right, now, if I say, I'll give you this same reaction, and I will. Same reaction. But I'm going to tell you, we're going to use a strong base. And I tell you, the E2 mechanism is operating. Do you remember from last week that the groups that leave have to be opposite each other? Remember that? They have to be anti-coplanar. There's only one product. I'm going to ask you for two products here. I'm going to ask you for one product here. the groups that leave have to be pointing in opposite directions. Okay? The groups that leave is a hydrogen and a halogen. If the halogen is pointing down, the hydrogen has to be pointing up. It cannot be pointing in the same direction. So there's only one product you could get. So just remember the severe limitations on the arrangement if the molecule is in a ring. So let's pretend that this is a halogen, the blue, and this is a hydrogen. So, and I want elimination by the E2 mechanism. They can't point in these directions. One has to be pointing up, the other has to be pointing down. Then they can eliminate. Now, if it's a straight chain molecule, it doesn't matter, see, because it can freely spin. So sometimes it's here, it's not going to react. But then other times it's like this, and this will leave, this will leave. See? So it has to be like this, one up, one down for elimination to take place, if it's by the E2 mechanism. Okay, so in a ring, you don't have the ability to rotate. So in a ring, these guys are locked in. And so the only product you can get, if I tell you we have a strong base and an E2 mechanism, this has to leave, it's pointing down, the hydrogen at least has to be pointing up. You can only get the double bond on the left side. You don't get double bond here. You're not going to get two products. So keep that in mind. No restrictions on which directions these guys point in space for the E1 mechanism that can both be pointed down, or one down, one up, it doesn't matter. These guys can leave, these guys can go. These are across from each other, these are the same side, it doesn't matter. For the E2 mechanism, though, the halogen that leaves and the hydrogen that leaves have to be pointed in opposite directions. With the ring, they're locked in. With a straight chain compound, doesn't matter how I draw it. If I draw it like this, don't worry, you can still get elimination, because this is free to spin. So that's something we learned about last week. I think that covers pretty much everything we got up to last week. Any questions so far?
Dr. Ward?
Yes.
I'm kind of confused about that. Like, the second product that you got for that, which product did you take out? You took out the...
I got the X of the halogen. And then next door, I have a hydrogen, so I can take out this halogen and this hydrogen, get it up on here, that was this. And I could take out this halogen and this hydrogen, and so the double bond goes here.
Oh, okay, so that flipped.
And so these two can leave, give me this product, or these two can leave,
Okay.
give me this product. And it doesn't matter, now you can't see what they got here. It doesn't matter if these two are the same side, they can still leave and give me this product. It doesn't matter if this is pointing down, this is pointing up, they can still leave. For E1, it doesn't matter which direction in space they're pointing. For the E2 mechanism, the groups that leave have to be pointing in the opposite direction. So these two can leave, but these two cannot leave. They're not opposite each other. And I'm not free to rotate because I have a ring, so you can't rotate that to get them opposite each other.
Sorry, I wanted to ask something I didn't earlier. The two products from E1, so they're different. They're basically different.
Yeah, there's different
properties.
Yep. Slightly different. I mean, not terribly different, but slightly different. The other thing you want to remember, stability of alkenes. Remember that? The most stable alkene has R groups. The more R groups you have on the carbon that's double bonded, the more stable it is. So the least stable alkene is ethylene. It has 4 hydrogens. That is the least stable. That's the least likely to form. Now, what's a little bit more stable is if you have 3 hydrogens and an R group. Now, don't be shocked or surprised. This R group can be a 1 carbon fragment, a 2 carbon fragment, a 50 carbon fragment. It doesn't matter. They just call it R. So this can be a methyl group, ethyl group, a propyl group, a butyl group, a pentyl group. It's just, the rest of the molecule. Yes?
Is that why polyethylene doesn't really occur in nature? It's because it's...
It's too reactive, yeah.
Oh, okay.
Yeah.
Cool.
Yep. Ethylene does, but it's not that stable.
But not as a polymer.
No, yeah, but not as a polymer. No, that's something that's, all these plastics and things, you won't find plastics in nature. That's why they don't degrade that well, because they're not natural. There's nothing to eat them. They are synthetic. Once you make them, you can't get rid of it.
Yeah.
It's forever. Okay, so this is more stable than this one, and then this is even more stable. If I only have 2 hydrogens attached to carbons and 2 R groups, this is more stable. I could also have it like this: a hydrogen and a hydrogen. See, these are about equal stability. So this is the least stable. This is more stable. These 2 are more stable. So basically, the more R groups you have attached to the carbons that are double bonded, the more stable it is. Another way of looking at it is the less hydrogens you have, the more stable it is. And the most stable alkene will be one that has no hydrogens attached to the carbon has no bond. So just remember that. If you have a choice to where a double bond goes, make the most highly substituted alkene the product of choice. That's the way it works. Okay? And lots of times you do have a choice. So I'm going to ask you for the major product. So for instance, if you have this, and you have a halogen, let's put bromine here, and let's add a strong base. And I tell you that substitution will take place. This is the B. And it's the, I'm sorry, elimination, and substitution break, elimination. So what is going to be the product? Now, it doesn't matter what directions I point him in space, because this is free to rotate. So, I mean, it won't react until this is down here, this is down here. It doesn't matter. It's a linear compound, you got free rotation. But do you see that there's 2 potential products for dehydrohalogenation? I would lose a halogen and maybe this hydrogen and get the double bond here, or I could lose this halogen and this hydrogen and get the double bond here. And you're going to get a mixture. One would be the major product. So I'm going to ask you which is the major product. One way to do this is to see how many hydrogens are attached to these carbons. And so, remember, the more R groups you have attached, the more stable it is, or the fewer hydrogens you have attached, the more stable it is. So however you want to remember it, but these double bonded carbons have 1, 2, 3 hydrogens attached to it. These double bonded carbons only have 2 hydrogens. So this compound is more stable. You always tend to form a double bond in the interior, if you can, rather than the end. So if I ask you for the two products, and then I say which is the major product, and these are the 2 products you get, then tell me this is the major product. Now, this is what those who take lab, this is what we did in the lab this week. Instead of having a halogen here, you can have a hydrogen, right? So instead of starting with this material here, we just did, you can also do this. OH. Now OH is a bad leaving group, so you're going to have to add an acid, sulfuric acid or phosphoric acid, and heat it. So protonate the OH, this is in water too. You'll protonate the OH, then it can leave, and you form a carbocation. Remember, you still have a hydrogen here and a hydrogen here. And then